Hello everybody, Dr. Y here. Welcome back to my channel. Today I want to explain to you the idea of probabilities and conditional probabilities using a more visual type of representation that I believe helps people understand it better in case you have trouble grasping these concepts the way they're taught in a more usual fashion. Here's the idea. Imagine that we have a dartboard, a square-shaped dartboard, which is, I'm going to call 1 by 1, be it whatever measure you like to use, 1 by 1 meter or yards. And let's say that over here, more or less, there is a dart thrower, some device that is run automatically. It's going to shoot darts towards this board. And I'm going to assume the following conditions. This gun that shoots darts never misses the board, so it always sends the dart inside the square. And the way it shoots, when I click the button for it to shoot another dart, what it does, it randomly picks a position left to right and randomly picks a position up and down so that it's equally likely to hit any point, any location on this dartboard. Okay? So if I push a button and let it shoot, and I don't tell you where the thing fell, but if I ask you the question, what is the chance that the dart fell inside the square? You're going to answer, well, 100%, because I just told you that it never misses the square, right? We can write it this way, probability, right, inside the square. So this notation P and something in parentheses indicates the probability of that thing taking place. And this thing is normally referred to as an event, something that happened. So that probability equals 1, or if we rule 100%. So far, so good, right? Now imagine that I take this and divide it precisely in the middle. And then I push the button again. I don't know if that's precisely in the middle, but let's say it is. If I push the button again, and I ask you, what is the chance or the probability that the dart hit on the left side of the square, right? To the left of this middle line. You say, well, it's 1/2, right? Because they're equally big, and this dart throwing machine shoots darts in every direction, right? Equally likely. So the chances are going to fall here is the same as the chance is going to fall over there, and this is 1/2 and 1/2, right? So the probability that the dart falls on the left is 1/2, right? And the same for the right. Now, I'd like to think of these probabilities as ratios of areas. Right? If this is a 1 by 1, that means this is a 1/2 distance, right? And this is a 1. So the area of this rectangle is 1/2 times 1, which is 1/2. And if I take the area of the event that I am interested in, that is the dart falling on the left, divided by the total area of where it could have fallen, which is the whole square, I'm going to have, right? This area is 1/2 divided by the total area is a 1 by 1. It's a 1, which is the 1/2 that we had before. So there's nothing new there. But I just want you to keep this calculation in mind. Think of these probabilities as ratios of areas. And you'll see why in a little bit. So now that I have this 1/2 and 1/2, I could actually start to give names to these things to make it more interesting. I could call this side heads and tails. So what this is representing now is the toss of a fair coin. I tossed a coin. What is the chance I see tails? Well, that's the same as what is the chance that this dart throwing machine will shoot a dart and the dart will fall on this side. It's the size of that area divided by the whole area, 1/2. Right? Great. Now imagine that I'm going to throw or toss 2 coins. The second one is going to divide this area in heads and tails again. Now, if I ask you, what is the chance that when I toss two coins, I see two heads? Well, the first coin has to be head and the second one has to be. So this is equivalent to asking, what is the chance that the dart will fall in that corner little square, right? Well, this side is 1/2 and this is 1/2. So this area is 1/2 times 1/2, which is 0.25, divided by the whole area. This is quarter, right? So the probability of heads and heads is the 1/4, right? Over 1, if you will. Now, imagine if I ask you the next question, which is, I've tossed two coins, and I know that the result was the same for both, right? And then I ask you, what is the chance it was two tails? Well, the result was the same. It means it's heads and heads or tails and tails, right? And that means, this is me saying the dart fell either here or here, right? Because I told you, the only thing I told you was it's the same result for both. But I'm asking, what's the chance it's two tails? Well, the chance it's two tails is, what is the chance the dart fell there? Well, that chance is 1/4, right? But I told you that it could have fallen either here or here, right? So knowing that it fell either here or here, the chance that it fell here, right, because everything is equally likely, is this area divided by this plus this, right? Because it could have fallen here or here. So, but that's also 1/4, right? So that one plus this one, and that's 1/2. Which makes sense because, you know, it's 1/2 of the potential area. Good, now we could make this more interesting if I told you, well, one of these coins is biased. It's not really 1/2 and 1/2. So imagine that we could go in here and say the second coin is not a 50-50 chance of landing heads and tails. Let's say it's a 25% chance heads, right? And 75% tails. How about now? So what is the chance it's two heads? Same idea. You keep using the principle. This is 1/4, right? Because 25%, 75%. This is 1/2. So it's 1/4 of 1/2, right? So the probability with the biased coins of heads and heads, biased, is the size of this area divided by the whole area, which is 1. So it's 1/4 times 1/2, which is 1/8, or 12.5%, right? Great. And I could have done the same calculation. What if I told you they're both the same, right? And now what is the chance of two heads? That one is not as simple as this anymore because now you have these two areas of a different size, but you could do the same idea. You calculate this area, because I told you the dart landed here or here. But what is the chance that it landed there, knowing that it's in the shaded area, right? So it's the ratio of that area over the total of the two shaded areas. Right? So as you can see, you can think of these areas and that can help you calculate certain things in a more visual manner. Great. And we could do, other variations of this. We could talk about, dice, right? If I have a 6-sided die, you can think of that as dividing the 1x1 square into 6. And you could roll 2 of them, right? which means you'd be dividing something like that. And then you could be asking questions, what is the chance that, you know, the sum is bigger than 8? Well, we can calculate all of these sums and see which ones are bigger than 8. So let's say that is going to give you sum of these over here, right? And then say, what is the area of those divided by the whole thing? So the idea of the areas applies there as well. All right. Great. So the next thing I want to talk about is the idea of conditional, right? We talked about this a little bit already, in the sense that I was saying, given that I told you it fell somewhere, what is the chance that this other thing happened, right? So when you're talking about conditional probabilities, the notation is a little bit different. We use the following notation. It's the probability of some event A happening, where A could be heads or, you know, a die roll turning up a certain number. And then you use a little bar like this, and this bar means given, and there's an event, another one, right? So when I ask you that first question, what is the chance it's 2 heads, given it's equal, right? Either heads, heads, or heads, tails. I could have written that as, what is the chance of heads and heads, given, right? It's the same outcome. Right? And the idea is, well, I first figure out the size of this same outcome. And then I figure out what is the chance that of the event that I want, right? And then I divide that by the whole thing. So this is the idea. And that gets you the formula that you know, or you might have seen in class, which is you transform this into what is the chance that A and B happened, and you divide that by the chance of B. Right? So let's see an example of that here in the context of some machines, right? And here's a story. Let's say there's a factory that produces something. And there are 2 machines making products, machine A and machine B. So the production of this factory is such that 60% of the products are made by machine A, and 40% are made by machine B. All right. So this is me asking you, when I shoot a dart, there's a 60% chance it's going to land on the A side, and a 40% chance it's going to land on the B side. So more or less something like this, right? Imagine that this is 60% of the area, and that is 40% of the area. Now, when I make these products, I test them. There's a quality control operation at the end. And this quality control operation says the following. 2% of the products made by the machine A are defective on average. And 1.5% of the ones made by B are defective. So there's this event called product was defective. I'm going to call this the D event. Right? And when they say that, oh, 2% of parts made or products made by machine A are defective, they're essentially saying the probability that it's defective given that A made it, right, is 2%. So this is some data they gave us. And they also say the same thing about B. The probability that it is defective given that B made it, because I'm testing them out of the machine as they come out, is 1.5%. Great. So what does that mean in terms of this picture? Well, think about it this way. Defective is another slice in this universe of events. it slices the universe into products that are defective and products that are not. Just like this slices in products that are made by B and products that are made by A. So it's like I could slice it more or less like this, right? And then I can say the things inside, right? The colored area, be it red or yellow, they're defective. And the ones outside are not. Why did I paint them different? Well, what does this mean? This means the following. Given that your dart fell in the A side, the chance that it is defective, that is the chance that it fell in this red part, is 2%. Okay. And the other one, given that if I tell you in advance, I shoot a dart and I tell you it fell in the B part, then you go, oh, therefore the chance that it fell inside the yellow part, that is defective, is 1.5%. Okay? In other words, what this means is that the red is 2% of the A. And how big is the A? The A is 60%, right? So the size of the red, right, here, is 2%, oh, one more zero, 2% of 60%. Right? 2% of 60% is 1.2%. Great. And the size of the yellow is 1.5% of 40%. So this guy here is 1.5% of the size of B, 40%, which makes it be 0.6 of 1%, right? Because it's 40% of 1.5%, that is, it's less than 1.5%. Good. So if I were to ask you, if I pull out of this production of today's products, in which 60% came from A and 40% came from B, pull a product at random, I don't know who made it, which machine made it. What is the chance that it's defective? And if I ask you that, I'm asking you for the P of D with no condition, right? Well, for that, you simply have to calculate, oh, how big is the painted area? Counting both the red and the yellow. But we got that already. We just did the calculation. I know the red is 2% of A and the other one, right? So the probability of D is the size of this guy in relation to the whole box. The box is 1. Right? So that is 1.2% plus 0.6%. 1.2% plus 0.6%, and this is 1.8%. Okay? Now comes a variation of this. Sometimes we are given a conditional in a certain direction, given a, what is the chance of defective? But we're actually interested in the opposite. That is to say, but what I really want to know is the following. If I pull a product at random and it is defective, and I know the chance of that happening is 1.8%. And let's say I pull the product and it is defective. What is the likelihood or chance or probability that it was made by A, right? Well, notice that this is the flip side of that one, right? This one is, I told you it came from A. What is the chance it's defective? And now I'm asking you, I picked one, it's defective. What is the chance A made it? Well, here's the idea. In terms of thinking of the areas, and then we'll see the formula. Given D means I shot a dart and it fell in here. Right? I tell you. Knowing that it fell inside the painted area, what is the chance that it fell on the side of A? Right? And again, because these darts are equally likely to land anywhere, knowing that it fell in this little area here, the chance that it fell in the red is simply the ratio, how big is the red, over the whole thing. Right? Well, the red I know is 1.2%. 1.2%. And the whole thing is 1.8%. Right? This is like 12 over 18. If I divide by 6 above and below, I get 2/3. All right? So this is how you can flip these probabilities around by simply thinking of this dart falling somewhere, that being your conditional. I know it fell here. What is the chance that it also fell over there? And taking ratios of areas. Now, you might have learned this as Bayes' rule or Bayes' theorem. And the formula for that is if you have something given something, what you do is you take the flip side of that. You multiply by the second guy, and you divide by whatever was after the given in the first place. And if you see, this is exactly what we did, but in a more visual way. In some sense, this is giving you some visual intuition for why is the formula what it is. Because P of D is the size of the color gun, right? 1.8. And this 1.2 came from where? Well, knowing that it's on the A side, meaning the 60%, what is the chances defective? It's the 0.02. So 0.02 times the 60. Okay. So we effectively did the calculation the formula prescribes, but not thinking of the formula, thinking of the picture. And that's the idea. So I hope that this is a little more intuitive for some folks that like to see things, in pictures and graphs. And I like to think of it that way a little better. But then it also helps you remember what the formula is, right? Great. So I only do one more, and I'll close this explanation with one more example. And this example is in the context of tests for diseases, which is something that is, we all know very well in these current times. But this particular one is about allergy to cats, or cat hair, or allergy to pets, right? So imagine the current story. As I erase here, I need to entertain you with something. I might as well tell the story, right? So here's the story. Let's say we're talking about allergy to cat hair, which lots of people have. And some of them can't have a cat because of that, which is sad, but it is what it is. Now, let's say that it is known that about 5% of the population are allergic to cat hair. So I'm going to call this event, being allergic to cats, A for allergic. So probability of being allergic is 5%. Great. And there's a test that you can run, which is pretty accurate. Here's what happens. For the people who are allergic, right, given that you are allergic, and I know that because I can look at the track record of the test and then look at the experiments they ran and everything, the chance that the test will return positive, right, the plus is going to be my positive, is 80%. Okay? So pretty good. And for the people who are not allergic, and I know these tests are never perfect, they make mistakes, they have the false positives. The people who are not allergic, and in math that symbol is kind of an, fallen down L. That symbol means not, right? So if you see that, that means not the following. So if you're not allergic, the test can still return a positive, and let's say the chance of that is 10%. Okay, so let's say my daughter, who loves cats, goes to a friend's house, and she comes back all, sniffly and itchy, and oh man, maybe she's allergic to cats. So I take her to take this test. And the test comes back positive. And I'm like, what does that mean? And I look at the track record, and this is what most people, conclude. Oh man, the test is 80% accurate, so there's an 80% chance she's allergic to cats. Well, wait a second. What this says is the following. The world is divided into two types of people. Those who are allergic to cats and those who are not. So let's take the world, the universe of all possible outcomes, my square, where I'm shooting these random darts. And just to make this big enough for us to visualize, this is not to scale, but let's say this is 5%. So this, strip here is my allergic people, and this not allergic. Okay, so this is 5% of the whole area. Great. Now, what this says here from the data that we have from the test is, given that you are allergic, right, the test is positive 80%. That is to say, when I give someone a test, the test also splits the people in the universe into two kinds. The ones who test positive and the ones who test negative. So it's like I did something like this, right? And I have a piece of this that falls over there, and a piece of this that falls over here. So if you're in the colored part, the test returned positive for you. And if you're in this non-shaded part, be it here or there, it's a negative, right? The painted area means the test is positive, right? So positive test equals inside colored area. Notice that a piece of it is inside the allergic side and also inside the non-allergic, because still, right, even if you're not allergic, sometimes it comes back positive. Great. So what this 80% means is the following. Given that you are in the allergic part of the universe, so if I shoot a dart and I tell you it fell somewhere in here, and the chance that it fell in the red part is 80%, that is only true if the red part is to be 80% of this total area of that strip, right? So the size of this red area is 80% of this A area, which is 5%. Right? Because I'm telling you with this statement that the likelihood, if I shoot a dart and it falls in this A rectangle, the likelihood it will have fallen in the red part of the A rectangle is 80%, which means this area has to be 80% of the total area. And that is 4%. Okay? Great. And the next statement refers to the yellow part. If I shoot a dart and I tell you it fell in the not A area, and then I tell you the likelihood that, given that it fell in this part, the likelihood that it fell in the yellow part is 10%, well, that is only possible if the yellow part is 10% of the total not A part, because these darts are being thrown or shot at random, and they're equally likely to fall anywhere. So the size of this yellow part here is 10% of the size of this not A area, which is, well, who is not allergic? The rest of the population, 95%, right? So 10% of 95% is 9.5%, right? 0.095. Great. So now if I were to ask you, what is the chance that I take any person at random and test that person, and the test will come back positive? Well, the chance of positive, and positive being the colored area, is the likelihood that if I throw a dart, it'll fall in here. Well, but that's proportional to how big is this area in relation to the universe, which is area 1. It's simply the sum of the red and the yellow. That is 4% plus 9.5%. This is 13.5%, right? Make sense? Great. So back to my story. My daughter comes back feeling a little sick, and I test her, and the test is positive. Now I'm debating, what is the chance she is allergic? So what I'm asking myself is the flip side of this. I'm asking, given that she tested positive, right? What is the probability that she is allergic? Which is not that, okay? Well, same idea. Think about the darts. If I throw a dart and I tell it, it fell in the painted area. So your question is, given that it fell in the painted area, what is the chance that it fell in the red piece of the painted area, right? Well, there's just a ratio of the area. How big is this red in relation to everything? Well, the everything we know, right? We just added the red plus the yellow. So this is my 13.5%. And the size of the red, we know it's 4. I can't do that calculation in my head right now, but I pre-calculated. This is roughly, and that little tilde symbol above an equal sign means approximately equal to 29.6%, if I recall correctly. Right? Again, we are flipping a conditional to another direction, which was the one of interest. And this is, similarly to the previous example, an application of Bayes' rule, because what we essentially did here is we calculated the reverse conditional. Right? To get this guy, you take that one times the chance of A, which is what we did here, divided by the chance of positive, which is the size of these two areas. But again, I feel like this is a little easier to understand or visualize because we're thinking of these concrete, spaces and darts being shot. All right? Great. So this is all I wanted to say about conditional probabilities, Bayes' rule. I hope this is useful and helps some of you get a little more intuition about these concepts. If you like this video, please give me a thumbs up, leave a comment below, and if you haven't yet subscribed to the channel, please do so. It helps me get noticed and have the YouTube engine suggest my videos to other people and helps me keep going with more videos like this. Thank you very much. And for now, it's goodbye from Dr. Y. See you later.